Hey everyone, welcome to Calculus 2. This will be lecture 13. In this lecture we're going to continue with some applications of integration, and this will be a little bit of a left turn though from what we have been working on. Differential equations, strictly speaking, is a whole domain of investigation. It's not merely an application of integration, though it is a natural. It can naturally be jumped into and thought of as such at the onset. But differential equations is a whole field, vast area of study. And in Calculus 2, we usually touch on it. We usually introduce it. But we introduce it as a kind of more of like a preview of what's to come. Differential equations actually is an entire standalone course. Which you'll typically take after Calculus 2 or possibly after Calculus 3, depending on sort of your inclination. But for this lecture and the one that follows this, we're going to be doing just a kind of an introduction to differential equations. Okay. And I think it's smart to do that. I think it's a good idea to do that. It gives students a sense for where that differential equations course goes and in kind of the direction it takes. So I think it's a good idea to just kind of briefly touch down on the differential equations landscape a little bit in Calculus 2. So with that, let's get started. So we'll call this section 2.5, and this will be differential equations. And we're going to actually talk about a very specific family of models that are technically differential equations, and those are going to be growth and decay models. Okay, so that is what we're up to here. So let me double check that this is nicely focused. Okay, so so up until now, I mean, we've talked about differential equations here and there, not really in any kind of systematic way. Up until now, we have looked at a few. So we've solved only two types of differential equations. Okay, so what are those types? Well, the first type we looked at was this, where you've got y prime equals some function of x, right? And then the other one we looked at was where we had a second derivative, y double prime equal to a function of x. Okay, so these are the only two we've looked at thus far. Obviously, differential equations can get as crazy as you can imagine. They can be any old thing could be a differential equation. Really, what we mean by a differential equation is just an equation that contains variables which represent derivatives. Okay, so there's going to be a huge multitude of different strategies for solving differential equations. What we're going to study in this section and the next section is one such method called separation of variables. So this is the general strategy that we will be using / learning. And just like with with algebraic equations, there'll be lots of different strategies like factoring, quadratic equation, that kind of stuff, substitution. There'll be lots of different methods for solving those types of equations. And the same is true for differential equations, though the methods are more complex and more involve calculus. But the first method that pretty much everybody learns is the separation of variables method. And so that's what we'll start with. Now, the next lecture, section 2.6, will be all about separation of variables, and we'll get into a lot of detail there. But in this section, we do need the ability to solve differential equations, so I'm going to introduce separation of variables very gently. right? And we'll get into the formalism, or something, not the formalism. We'll get into more the theory behind it and sort of the larger ideas in the next section, right? This is going to be more of a motivating section. So let's start with an example. Okay, so we're going to have some differential equation that we want to solve. So let's say we want to solve an equation that looks like this. Y prime equals 2x over y. Right? So this is obviously different than the functions, the differential equations we've seen before. Right? Over here on the right-hand side, we've only dealt with differential equations where the right-hand side was a function of x, and obviously that is not the case here. Okay? So in this example, the right-hand side is 2x over y, so it is not written as a function of x. Okay, so the general idea behind separation of variables is to get all of the y variables on one side and all of the x variables on the other side. Okay, so that's sort of the chief machination that's at work with separation of variables, hence the name, separation of variables. Y is on this side, x is on that side. Okay, so in this case, it's fairly straightforward to do that. So we start with y prime equals 2x over y, and it's a simple maneuver to get the variables separated out. So what did we do here? Well, all we did was multiply both sides by y. That's all we did there, of course. Just a little algebra. Right, and then once the variables are separated out, once the separation of variables piece is accomplished, then we can use integration to solve the differential equation, right? And so the way that would work in this case is we would integrate both sides with respect to x. Okay, so let me just make a note of that. Integrate both sides with respect to x. Okay. And so what does that mean? Well, we've got the integral of y, and then y prime, remember, is dy over dx. Okay, now notice what happens here. You've got sort of this sleight of hand cancellation that takes place, and we end up with y, the integral of y dy equals the integral of 2x dx. Okay. And then, of course, we can integrate, right? So this side over here becomes 1/2 y squared, and this side over here becomes 2x squared over 2. Okay, and let's throw a constant on there. We'll talk about the constants in a moment. Right, but then you can see we could clean this up really nicely. 1/2 y squared minus x squared equals c1, and we could say that, let's clean it up even better and say y squared minus 2x squared equals c1. Okay, so that's kind of a nice way to write it. And then, so what we would say is that this is a solution to this differential equation, right? We'll get more into the sort of the big idea behind solutions of or solutions of differential equations in the next section, and then also more so in the differential equations course. But kind of from our standpoint, early standpoint, we can think of a solution of a differential equation as being an equation that we arrive at that does not contain any derivatives, right? That is written, it is purely base functions, right? No derivatives whatsoever. Okay. Now let's talk about the constant here, the constant of integration. So notice, right, if I go back a couple steps and I've got my integral of y dy equals integral of 2x dx, right, and I go back to that. If I integrate this and I put a constant on both sides, okay, like so, right, you can see that I could easily then do the algebra here, and I would get 1/2 y squared minus x squared equals c3 minus c2. right? And then technically I could just kind of put this in the, I'm aiming for the same form here as what the previous solution was. So I could say this is y squared minus 2x squared equals c3 minus c2. Now that's basically the same thing as I have up top here, right? So notice you've got the c1, and over here you've got the c3 minus c2. Right, so what we generally do is we just toss the constant on one side, right? So we don't need to add a constant of integration to both sides. As you can see, you get the same result. Okay, and so what we could say is the solution is really y squared minus 2x squared equals some constant, right? So you can drop the subscripts and just write a single c. Okay, so that's the story with the constants. Now this equation here, this is the solution to our differential equation. Now, that being the case, we ought to be able to differentiate this and get back to the original equation. And so we can use implicit differentiation to confirm this solution. Okay, so if we do that, right, we would say ddx of y squared minus 2x squared equals ddx of the constant. Okay, and so technically we would want to differentiate each piece here, right, like so. And so this part here, remember this is, we're differentiating y with respect to x, so we would say this is 2y times y prime, and over here we're differentiating x squared with respect to x, so this would be minus 4x. Okay, and over here, of course, the constant differentiate, when we differentiate a constant, we get 0. And so then just kind of taking this equation and solving for y prime, we ought to get back to where we started, right? And so we'd have 2y y prime equals 4x, and we'd see that y prime equals 4x over 2y, and further that y prime equals 2x over y, right? And so that is the initial differential equation. Okay, perfect, right? So that's where we started. That's what we would expect, right? If we solve a differential equation by using integration to get rid of the derivatives, then we ought to be able to reverse the process by differentiating. Okay, good. So sometimes the notation can get a little tricky here. So Leibniz notation for the derivative, Leibniz differentiation notation, is sometimes preferable with separation of variables. It's somewhat more intuitive, right? So the previous example, y prime equals 2x over y, right? You could also write this as dy dx equals 2x over y. And then we can see very easily that y times dy would be equal to 2x times dx, right? And then we would just say, oh, integrate both sides, right? And then you get the integral of y dy equals the integral of 2x dx. Right, so it's somewhat more intuitive. It kind of bypasses this sort of tricky maneuver here, which isn't that, I mean, this isn't tricky once you've done it once, but it's sort of strange, right, that you're kind of canceling these things and it's a little unintuitive. Whereas this notation is very slick and straightforward. Okay, so sometimes this notation is preferred. Right, and so it's up to you, right? If you are facing a differential equation, you have a y prime in it, or you can choose to convert it to dy dx if you think it's better. However, you could also probably solve this equation using the original notation as we did. It's kind of, up to you. So, okay. All right. So this was an introduction. To separation of variables. Just an introduction. As I say, we need to, in order to motivate some of the things that we're about to talk about, the growth and decay models in particular, we needed to have, at least some sense of how to solve a differential equation. And the next section, the section that comes after this, will delve deeper into the separation of variables idea, and we'll kind of develop it a little more rigorously and thoroughly. Okay, but for now, that's enough to get us into some examples here. So let's talk about growth and decay models. Models. Oh my goodness. I assure you, I knew how to spell models. Sometimes I write faster than I think, or maybe it's the reverse. I'm not sure. But anyway, so in many applications, we'll see a couple here in a second. The rate of change of a variable is proportional to the value of the variable. Okay, so in many applications, the rate of change of a variable is proportional to the value of the variable. Okay, so when we say rate of change of a variable, what we're talking about is a derivative. And when we say proportional to the value of the variable, what we're talking about is a constant times the variable. Okay, and so a lot of times you'll see things that look like this: dy over dt equals k times y. Okay, this side over here is the rate of change of y with respect to time. Usually we use the dt for time. And of course the equal sign you can interpret as the word is, basically. The rate of change of y with respect to time is, and then this piece over here is proportional to the value of y. Okay, so in this sort of equation, you've got the rate of change of y with respect to time equals k being some constant and y being the variable. So the rate of change of y with respect to time is proportional to the value of y, right? And of course, this k is very crucial in establishing models. So here, k is a real number and is called the constant, or the proportionality constant would be fine. The proportionality constant. That's a way to refer to k. Like it's the constant of proportionality constant. Okay, so an equation like this is obviously a differential equation, right? This is y prime equals k times y. So this is a differential equation, and this differential equation is very common. It's very common in you'll come across this, and if you go into the sciences, you'll see this sort of thing all the time. And it has a general solution, okay? Meaning that equations of this form can be solved by using kind of the form of the solution. So let's talk about that for a second. Okay, and we'll just write this out as a theorem, and then we'll go into the derivation. So if y is a differentiable function okay, such that y is greater than 0 and y prime equals k times y, okay, for some k and r, okay, then y equals c times e to the kt power is the general solution for this differential equation. Is the general solution for the differential equation y prime equals k times y. Okay. Okay. And so as we kind of said above here, k is the proportionality constant. Now c in this case, c is called the initial value of the equation. Now, what does that mean? Well, initial meaning starting, right? So if you can see here that if t is equal to 0, then e to the k times 0 is just 1, and so y is equal to c, right? So at time, okay, at time 0, meaning at when t is equal to 0, y is equal to c. Okay, so that's kind of what we mean by initial value. We'll get into that later, probably next time. A little bit this time. But that's a whole range of problem types for differential equations are called initial value problems, and we'll see a whole bunch of those. But let's see, where did this solution come from? Where did y equals ce to the kt come from? Okay, so basically I want a proof here of this theorem. How did this come about? Okay, so let's talk about that. So we'll put proof here. If y prime equals ky, then we can separate this out here. We can and we can write y prime over y equals some constant k. Right. So this is the separation of variables piece, isn't it? Right. You get all the y variables on one side, and all of the x variables, in this case it's just a constant, on the other side. And then we can take this thing and we can differentiate both sides with respect to t. And so you get y prime over y dt equals k times dt, integral of k dt. Okay. And similar to the method we had before, we can write this as dy over dt. So dy over dt all over y times dt equals the integral of k dt. Okay, so just integrating there. And then, of course, the dt's will cancel, and you would get the integral of 1 over y dy equals the integral of k dt. All right, and then at this point we can we can integrate here, right? And remember, y is greater than 0, right? That's part of the theorem. And so that means the integral here is the natural log of y, and that's going to be equal to t plus some constant. Just put c1 there. Oh, sorry, kt. There we go. So you got the constant, and then the integral over here with respect to t is just k times t. Okay. All right. So now we've got this equation here that has, no derivatives in it, and so this is, this is quote unquote a solution, but we could clean it up a whole lot. And so the old trick here is to use the exponential here, like so. Okay. And then on this side, e raised to the ln of y is just y. And over here we can break this into two pieces. All right? So remember, if you're adding in the exponent, then you can break that apart and it becomes a product like this. Okay. Now notice that e to the c1, right? So c is some constant, and that means we're exponentiating e by some constant. And so what we can do here is we can rewrite e to the c1 as just your c, right? So whatever that c1 happens to be, you can easily rewrite it as just a c, e raised to that constant. Okay, and so that means this here is y equals e to the kt times the constant, right? Whatever e raised to c1 is. Okay, and then slightly better way to write this might be y equals c times e to the kt, right? And that's sort of, what we were driving towards, right? That's the that's the general solution that we laid out in the theorem. Okay, so what does this mean? Well, so all solutions of y prime equals k times y are of the form y equals c times e to the kt. Okay. All right. Very good. Okay. Okay, so that's the kind of the walkthrough of this first general solution to differential equation. Okay, and now one thing I forgot to mention with regard to this k, which I should mention, is that depending on the value of k, your model is either going to reflect growth or decay, exponential growth or exponential decay. And so I'm sure you could guess, but exponential growth when k is greater than 0, and then exponential decay when k is less than 0. And of course, static, not moving at all, when k equals 0. So totally uninteresting example would be k equals 0. Then it's just y equals a constant, right? So okay. So let's talk through an example here and see how some of this kind of fits together. Okay, so this is our first example. So we'll write the rate of change of y is proportional to y. Okay, so that's our first indication. That means basically y prime equals ky. Okay, so the rate of change of y is proportional to y. And when t equals 0, y equals 2. When t equals 2, y equals 4. And then the question is, what is the value of y when t equals 3? Okay, so we're given two kind of initial values here, t equals 0 and when t equals 2, and we need to know what happens when t is equal to 3. Okay, so we know that the equation here, because we know the equation is y prime equals ky just based on the wording. The rate of change of y is proportional to y. And we kind of went through that's what this means. So the variables, the rate of change and the variable y are related via this equation here. And further, given that it's this equation, we know that we have the following: y equals c e to the kt. So what we need to know is we need to find the values of c and k. Okay, so we need to figure out what c and k are. Okay, and we're kind of given, you can imagine we're sort of given two sets of conditions, right? And that makes sense because we have basically two unknowns. So we're going to need two equations to solve for two unknowns, right? And that's what we're going to use. So we'll have y equals ce to the kt. Okay, and first we'll plug in t equals 0, y equals 2. So that means you'll have 2 equals c times e to the k times 0, right? Which so I'll just put a 0 up here. Okay, and what does that mean? That implies 2 equals c, right? Of course, 2 equals c times 1. The e to the 0 is 1. And so then c equals 2. Okay, so that's our first piece. So then to figure out k, we can use the other condition that's given, t equals 2, y equals 4. Okay, and so we would kind of do the same thing. So 4 equals c e to the k times 2, right? So t equals 2, y equals 4. But remember, we know now that c is equal to 2, so 4 equals 2e to the 2k. Okay, right? And so can we figure out what k is in this scenario, or in this equation here? Yeah, definitely. Right, we take the natural log of both sides. First, let's divide out the 2, I guess. So 2 equals e to the 2k. Then let's take the natural log of both sides. So the natural log of 2 is equal to the natural log of e to the 2k. Okay. And so that means the natural log of 2 is equal to 2k. Right? And then therefore k is equal to 1/2 times the natural log of 2, which has an approximate value of 0.347. Okay. Okay, so therefore the model has constants k equals 0.347 and c equals 2. Okay, so that means the model is basically this, right? It's y equals 2e to the 0.347t. Okay, so that's the model. Then what happens when t is equal to 3? Right, what is y equal to at time 3? So when t is equal to 3, we have y equals 2e 0.347 times 3. And we can just plug this into a calculator. We can figure out exactly what that value is. And having done that already, we see that it's approximately 5.657. Okay, so there you go. Okay. So that's a good first example, right? So we started with just the fact that the rate of change of y is proportional to y and some initial conditions, and from that we can spin out what the model must be for this scenario, and we can even identify values of y for additional values of t. Okay. Perfect. Okay, so that's kind of a nice initial kind of example, because it sort of shows you the role that these initial values play in differential equations, or some of the role, part of the role. That's the main role, right? So the main role of the initial values is to basically parameterize the model. We need to know what c is, we need to know what k is, therefore we have to have some initial values in order to derive those constants. Perfect. Okay, let's do another example, kind of a more real-worldy example, more realistic example, potentially. So example, suppose a population of fruit flies increases according to the law of exponential growth. So suppose a population of fruit flies increase according to the law of exponential growth. Okay, there were 100 flies at day 2 and 300 flies at day 4. So let's put that information in. There were 100 flies at day 2 and 400 flies at day 4. Okay, so right, you can, 300, should use the right numbers here, 300 flies at day 4. The question is approximately, obviously, how many flies were there in the original population? Okay, so here's a nice little example of a problem that's going to involve a differential equation. Right, we got a population of fruit flies. They increase according to the law of exponential growth. Right, this is a known. Say this is an assumption. We start with this assumption, and then we have sort of some empirical data here. At day 2, somebody went in and counted up 100 flies in the population. So inside the petri dish or the jar or whatever it is, inside the container there were 100 flies, and 2 days later there were 300 flies. Question is, how many did we start with? Okay, right, so suppose a population of fruit flies increase according to the law of exponential growth. That's code for y prime equals kt. Okay, and that of course means that y equals c e to the kt is our model. Okay, that's the model. Okay, and we have the initial conditions. So t equals 2, y equals 100. And so we'll start with that one, right? When we plug that into this expression, we get 100 equals ce to the 2k. Okay, and the other one that we know is t equals 4, y equals 300. Okay, so we could plug that in as well. 300 equals ce to the 4k. Okay, so we have these two models, and we'll just refer to this as equation 1, and this will be equation 2. It's frequently useful to number your equations. Okay, so from 1, we know that basically, basically you can divide both sides by e to the 2k. And so c is equal to 100e to the negative 2k. Right, and we can plug this into 2. Okay, so plugging that into 2, we start with 2 is 300 equals ce to the 4k. So that means 300 equals, instead of c, we'll put in our 100 e to the negative 2k times e to the 4k. Okay, and we can combine these, right? Just the same kind of trick as what we used before. So 300 equals 100, and then we're gonna, this is e to the negative 2k times e to the 4k, and so that's the same thing as e to the negative 2k plus 4k, like so, right? So it's kind of, I guess this will exercise your natural logarithm exponential function kind of skills, right? And so that means 300 is equal to 100 e to the 2k, and then of course from this we can solve for k, right? And so let's Divide both sides by 100, and we get 3 equals e to the 2k. And let's take the natural log of both sides. So ln of 3 equals ln of e to the 2k. And that means ln of 3 equals 2k. So kind of similar to the previous proportionality constant we derived. We get k equals 1/2 times the natural log of 3, which is approximately 0.5493. Okay, and so the model so we know that the model is y equals, let's see, let's see, what did we get? Oh, we have to figure out what c is first. First we need to know what c is up here, right? So let's see. So 100 equals c times e to the kt. So k we figured out was 0.5493, and then we need our t. So to figure out what, we haven't gotten there yet. I jumped the gun there. Right. So plugging in our k, we have this, right? Now we can use the initial condition to figure out what c is. Right? So this all means that c is equal to 100 divided by e to the 0.5493 times t. Now what is a t that we can use here? Well, when the population was 100, that was at time what? Time 2. Okay, so we can just use t equals 2 there. So that means c is equal to 100 divided by e to the 0.5493 times 2, which is 100 divided by e to the 1 point, let's see, I calculated it a minute ago, 1.099 approximately. And so c is equal to what? It's about 33. So if you do this math here, you'll see that this is about 33. Okay. All right. So now we know what c is. We can figure out the main question here. So let's remember what the question is here. So suppose the population of fruit flies increase according to the law of exponential growth. There were 100 flies at day 2, and there were 300 flies at day 4. How many flies were there in the initial population? Now remember, the initial population is going to be when k is equal to 0, right? So if our model looks like this, so our model will look like this: y equals 33 e to the 0.5493 times t. That's our model. So this is our population model. Then what was the initial population? Well, the initial population was 33, right? Because y equals 33 e to the 0.5493 t when t equals 0 implies that y is equal to 33 times 1, right? So 33. So the initial population was 33, approximately, 33 flies. All right, so that's the idea here. And so I don't remember if I used the terminology. Let me check here. Let me look back at my notes. Did I call? Let's see. Yeah, I did, actually. Good. All right. So here, when we were talking through this this theorem regarding this being the general solution to this differential equation, I did say that c is called the initial value Okay, right, so it's the initial value, and that's specifically because t is equal to 0 and y would then therefore be equal to strictly c. And that's sort of what we just showed. Okay, so this would be an example, right, because k is greater than 0. This is an example of exponential growth. Right, specifically the population of the fruit flies, right? They exhibit exponential growth. But technically speaking, we can say that this model is a growth model because the k is a positive value. Okay, let's talk through a decay model, an example using exponential decay. Okay, similar setup, but obviously different. But 4 months. So here's the example. 4 months after it stops advertising, a manufacturing company notices sales have dropped from 100,000 to 80,000 units per month. Okay. 4 months after it stops advertising, a manufacturing company notices sales have dropped. All right, specifically from 100,000 to 80,000 units per month. Okay. All right, so this is a decay problem, right? Something is decreasing. So if the sales follow an exponential pattern of decline, what will they be after another 2 months? So if the sales follow an exponential decline, what will they be in 2 months? Okay, another 2 months. All right, so that's the question. So we can use an exponential decay model. Okay, so we'll use the model y equals ce to the kt, where t is measured in months. Naturally. Okay. We know that c is equal to 100,000. Okay, since this was we'll say this was the sales at t equals 0. All right, that's kind of given, right? I guess it's sort of cloaked in the wording here, but it does say sales drop from 100,000 to 800,000 units per month, right? And so they noticed over a 4-month period that the sales went from 100,000 to 80,000. So the implication there is that at time t equals 0, sales were 100,000. Okay, and sales were equal to 80,000 at t equals 4. Okay. Okay, so sales were 80,000 at t equals 4. So therefore, what would we have here? We would have 80,000 equals 100,000 e to the 4k, right? We need to know what that proportionality constant k is. And, well, we can solve this pretty quickly. Let's divide both sides by 100,000. And we get 0.8 equals e to the 4k, like so. Natural log of both sides. Okay. And therefore, the natural log of 0.8 equals 4k, and so k equals 1/4 times the natural log of 0.8. Okay, and so k is going to be it's this value, natural log of 0.8 divided by 4. And if you plug that in, you can quickly get that. It's approximately negative 0.0558. Okay, and so that means then that our model is what? It's y equals 100,000, that's the initial value, times e to the negative 0.0558 t. That's the model. And so the question is, after 6 months, what should we expect our sales to be if indeed this is the model that reflects them? So after 6 months, we would have y equals 100,000 times e to the negative 0.0558 times 6, which is, you can just plug that in. This is, 100,000. This is just a number times another times 100,000. And so when you plug all that in, you get 71,500-ish. Okay, so sales will continue to decrease. This is an example of exponential decay. Right? So the case with the exponential growth is that, it kind of grows without bound, right? Exponential decay means that, the decay will continue, but it obviously, since this is a real world population or real world examples, the decay will asymptotically approach 0. Okay, so that is the idea here. All right. Okay, so that's a good place to stop. So again, this has been kind of an introduction to differential equations. Specifically, we were here looking at the example of y prime equals kt being sort of the relationship between the rate of change and the variable. Right, so here we said that y prime equals kt means the rate of change is proportional to the value of y, right? And this sort of relationship implies a model that looks like this: y equals ce to the kt, and this is what's called a growth or decay model, depending on the value of k. Right, and so that's kind of the idea, right? So we start with this relationship, and from that relationship, solving that differential. This relationship is a differential equation. We solve that differential equation, and we arrive at a model, and that model has enormously broad applications. Right? Pretty much everything can be, not everything, many things can be represented using growth and decay models, right? Population stuff in particular, very, very useful. Okay, so next time then we'll jump into a deeper exploration of separation of variables. Okay, so next time we'll get into this in more detail, right? And kind of this will be a true preview of the differential equations course that'll come after this one. All right, so we'll end it there.